Okay, so starting with Chapter 3 now, and I'll remind y'all before this weekend starts about the section on limits that we're momentarily skipping to come back to with y'all watching in a recording over the weekend. Okay, so Chapter 3, we won't need the limits business for Chapter 3 or for any of the sort of the beginning stuff of Chapter 4 that we'll get into. So it'll be fine. So linear algebra. So this is a course in multivariable calculus, of course. But we have several separate courses here at Duke in linear algebra. So why am I giving you a little bit of linear algebra here? Well, it turns out that if you know just a little bit of linear algebra, then you're armed to take a much more powerful and sophisticated point of view on the multivariable calculus. It gives you a language in which you can it's just better to talk about multivariable calculus in the language of linear algebra. This is why, by the way, the math majors who come in to Duke usually take this two-course sequence called 221, 222. 221 is linear algebra. They take a full course in linear algebra first, and then that gives them tools with which they can do, again, much more powerful things with multivariable calculus. Okay, we're not going to do all of that, but we're going to do a little bit. So I'm hoping we can get through all of Chapter 3 today. It's only 2 sections, and it's a little bit of an aggressive goal, but we'll see if it works out. Okay, so first thing I want to talk about is just to prepare you for why we need linear algebra, and that is let's consider derivatives. Right, let's think about single variable calculus, definition of a derivative, and by analogy, what would we sort of, first instinct, something to try, what would be our first attempt at defining a derivative of a multivariable function. So let's imagine we have a function from, Rn to Rm. And I'm just going to write some stuff down as a wild speculation, what seems like it ought to be right. Okay, I think I touched that with my elbow again. I'm going to have to get a little something for that. You would kind of think that f prime at some now vector x, now keep in mind, this is a point in the domain. The domain is now Rn. It's not just a number x, it's a vector x. Right? So, anyway, f prime, you'd think, I don't know, we're kind of working stuff out here. You would think it'd be a limit of, I guess it would be f of x plus h. Well, h now also has to be a vector, right? Because it's what I'm adding to x, also in Rn, minus f of x over h. And we'll take a limit maybe as h vector approaches the 0 vector. Doesn't that seem like a reasonable thing to write down as a definition? Until you take a closer look at what you've written down, by analogy, sort of ripping off shamelessly from Calc 1. Take a look at what you've written down and notice okay, I keep hitting the thing. I'm sorry, it's like my elbow keeps touching the thing. Sorry about that. Take a look at what you've written down and notice you've written down that you're going to divide by a vector. You might have noticed that's something we did not write down a definition of. And we didn't write down a definition of division by a vector because there is no such thing. And there can't be such a thing. There's no meaningful choice that can be made of what should it mean to divide by a vector. So we in our very first attempt to talk about multivariable calculus, it's a massive crash and burn failure right off the bat, right? So this is a big problem that we face. Or if you want to talk about multivariable calculus, some people would look at this and say, I guess you can't take derivatives of multivariable functions. This is a nasty problem. Okay, so anyway, here's what we do from this, and we'll do this in Chapter 4. We're just going to have to take a different point of view on single variable derivatives. And it's not an entirely different point of view. It's not like I'm going to tell you something you hadn't seen before, but we're going to focus on a different perspective that you have seen before of single variable derivatives, and we're going to try to generalize that different point of view on single variable derivatives. Again, details to come later. And when we try to generalize that different point of view, it's going to turn out that what derivatives are most fundamentally and naturally, they're not numbers. The most natural point of view on what a derivative of a multivariable function is it's this thing called a linear transformation. And it's going to take us a while to sort of build up to that. But it's ultimately, by far, the most natural point of view to take in this sort of a situation. So if we're going to try to get to that goal of understanding derivatives as linear transformations, which we kind of have to do. I mean, we certainly can't do this. Right? We need to understand what linear transformations are. So that's the first part of Chapter 3. The first section is about linear transformations. Okay, so here we go. What's a linear transformation? A little bit of terminology and notation first. Don't forget we write vectors vertically like this. Right? It's very convenient to write vectors like this. We saw, among other things, that it's very convenient to write vectors like this when you're adding vectors. Right? It looks great on the page. You just add coordinate-wise, and it's effectively like adding rows. Right? It works very nicely. So we're going to be using that a lot in this section and beyond. So just heads up, reminder. A quick definition. I'm going to define something called a linear combination of vectors. If you have a collection of vectors, a linear combination of those vectors is something of this form. So, in other words, it's what you get when you take those vectors, you multiply the vectors by scalars, and then you add. So anything that you can get by way of this process is called a linear combination. So I think the word combination is pretty easy to motivate because you're combining these vectors in certain ways, right? And linear because, well, you're multiplying by scalar constants only and adding. So you might say that these are operations that we think of as being linear in the sense that these are the kinds of operations that came up in our study of straight lines. Okay, so this is a very important construction. This construction is arguably the fundamental construction of linear algebra. So it's a big deal. I'm going to do a lot with this. And here's the first thing we're going to do with this definition of linear combination. We're going to use it to define linear transformations. Now I'm going to give you a different definition first to start with. But linear combinations are going to pop back up in a second. So here we go. Here's what a linear transformation is. First, let me disappoint you. A linear transformation is a multivariable function, and most fundamentally, that's what it is. It's just a function. It's not magic. It's not this more sophisticated object that we have yet to consider. It's just a kind of a function. That's it. Right? So multivariable function. Now, it's a multivariable function that has some special properties. A multivariable function that has the feature that when you add two input vectors, you effectively add their output vectors. Which is cute, right? I mean, not all functions do this. Quadratics don't do this. Right? So, kind of, amusing if a function might do that, you might say. And also, if you multiply an input by a scalar, you're effectively multiplying the output by a scalar. Okay, so a couple of cute properties to write down, and it turns out that any function that has these two properties, there's some amazing conclusions that you can draw, which is why we have this entire subject called linear algebra, which is, roughly speaking, about linear transformations. So, it's a big subject that comes about lots of powerful conclusions simply from a function having these two properties. So, that's all it is. It's all linear transformation is. Now, let's go back to linear combinations. Here's an alternative definition of a linear transformation. A linear transformation, multivariable function, that if you put a linear combination in, you get the same linear combination out. Now, I don't think this is a shocker of a sort of alternative to this definition. In this previous definition, we talked about, addition in, addition out, and scalar product in, scalar product out. If you think about it, linear combinations are just additions and scalar multiplications. So if a function, you might say, plays nice with vector addition, and if it plays nice with scalar multiplication, well, all that's going on here is an addition and a scalar multiplication. Well, two scalar multiplication. So it's pretty believable, I think, that this is true. It's also not hard to prove that these are equivalent. This is a nice exercise. I encourage everybody to give a shot. You know, assume that a function has these two properties. Show that it has to have this property. Right. All right, let me write that a little bit differently. If you assume these two properties, the way you would decide if it has this property is to take this expression and by way of the assumed properties, see if you can just rewrite it as what we want it to be. Right. If you assume properties 1 and 2, start calculating the left side of 3 and just get to the right side of 3. And it totally works out. Okay. And then vice versa. Okay. All right. Third fact, and this is a little bit more effort, but it's not that bad. Any function that has this property, any function that plays nice with linear combinations, right? Linear combination in, linear combination out. Any function that has that property has the same property for any number of vectors. It doesn't have to be just a linear combination of two vectors. It can be a linear combination of any number of vectors. And roughly speaking, you would prove this by applying the property 3, k minus 1 times. Not that hard to prove. Okay. All right. Let me draw a picture here of property 3. I think this is worth seeing. So what does it look like, in terms of the vectors themselves, to say if you put a linear combination in, then you get a linear combination out, and that's this picture that I have right here. So suppose you have a couple of vectors. There's V1. Let's suppose this is the image of V1. So this is T of V1. Okay. Now here's V2. Suppose this is the image of V2. All right. Now, I'm going to take a certain linear combination of these vectors V1 and V2. We're going to take about 1.5 V1s and about half of a V2. Right, that gives me this linear combination vector. There's the linear combination that we're going to put into this function. The assertion that I'm making is that when you take that linear combination, put it into the function, that what comes out will be the same linear combination, right, about 3/2 of the first one, about half of the second one, same linear combination of the otherwise output vectors. That's all this means. Right, so I think it abbreviates very nicely as linear combination in, linear combination out. Right, but anyway, that's what it effectively looks like. All right, everybody happy? Any questions? Okay. All right, so cool. A little bit of lingo. Very commonly, people say that such a function commutes with linear combinations. Y'all remember this term, commutes, right? So the A times B equals B times A, right? So whether you do the A first or the B first, you can do A first and then B, or B and then A, and it doesn't make any difference, right? So the idea of commuting is that you can change the order and it doesn't matter. Technically, when you talk about commuting, you're talking about the commuting of an operation. An operation acts on two things. It's the things that change position, right? So here, these aren't exactly things that are changing position. This is a couple of actions, you might say, right? So the act of taking a linear combination versus the act of plugging into this T function. And what we're saying is that those two things you can do in either order. You can take the linear combination. Here, let me go back to the algebra. You can take the linear combination first and then plug into the function, or you can plug into the function first and then take the linear combination, and that you would get the same thing either way. So it's a little bit of an abuse of the term commute, but it conjures the right image in the mind, and so it's a very common little bit of terminology. So now y'all have already heard me say, my own little variation on this. Instead of saying commutes with linear combinations, I say it plays nice with linear combinations. I don't know. I find that a little bit more satisfying somehow. But it's nobody else does that. That's just me. So you're going to hear other people say commutes with linear combinations. Yeah, everybody good? Okay. All right. Now this next example I have to do. It's a drag. This is a brute force. Directly check that a function. Here's a specific function that I claim as a linear combination, is a linear transformation, and I'm going to bluntly brute force demonstrate that this is in fact a linear transformation. It's just details. Right? But anyway, it's easy to get lost in detail, so I want to walk you through and show you how we go about actually drawing this conclusion that this function is indeed a linear transformation. Okay, now, here's what you can't do. You can't just look at the right-hand side and say, everything, looks linear. Nothing's being cubed, so there's no exponentials in there, so feels linear, right? That's not fair, right? You might say that's good intuition, and that's fine, right? But that's not a mathematical argument. Okay. Here's how the mathematical argument goes. We have to speculate on what happens when I put a linear combination of vectors into this function, and then I have to demonstrate that what I get out is the corresponding linear combination of the otherwise output vectors. So I need to show this turns into that. And you can see it works out, right? But anyway, we got to go through these details. Okay, so I'm going to write x like that, y like that, thus turning the linear combination into that, and then not hard to persuade yourself, just by algebra, that this is what it turns into. This is how you combine vectors. This is how you scalar multiply and then add those two vectors. Okay, that's the first part. Now notice what I have is I have a, let me use different colors. I have a first coordinate and a second coordinate that I'm plugging into the function f. Well, that first coordinate I need to put wherever I see an x1. Right? And this second coordinate I need to put wherever I see an x2. And so that gives me this. So this is just plugging in. This is just plugging into the function, right? This formula for the function is that. Just plugged in. Yeah? Everybody good? Okay. All right. Having plugged in, now I've got this great big algebraic monstrosity, and I just have to organize it. Now my goal is to show that it equals to this strategically. I mean, let's just think, what do I need to do in order to make this work out? You see that there's a bunch of factors, a bunch of terms with a bunch of factors. Some of these factors have some of these terms have an A in them. Some of these terms have a B in them. Clearly, I need to get all the terms that have a factor of A over on the left, and all the terms that have a factor of B over on the right. So let me just split those up. And this is just organizational purposes. Let me use different colors again. The terms that have the A's, just throw them all together over there. Factor out the A, you might as well. Right, and then the terms that have the B's, throw them all together over on the right, factor out the B. You get that? And lo and behold, we're done because that is exactly f of x, and this is exactly f of y. So, done. Now, tedious algebra, right? It's a real big yawn, but we did, in fact, prove that this is a linear transformation. Yeah? Well, so a cross product takes two vectors in, right? And so what we're talking about here is functions that take one vector in and then give a vector out. So it's a different kind of a thing. It's not. If it's an operation, you can define it in a way that would make it a function, but let's not. Yeah. So let's think of it as a different thing. Yeah. Right. Okay. Everybody happy? Well, let me rephrase that. I don't expect this to make anyone happy. Is everyone tolerant of what we've seen here? Okay. All right. Okay, so linear transformations, neat thing. It's nice when a function has this property. Let me emphasize, this is a special category of functions. Not every function has this property. I mean, not even close, right? We already made the observation, for example, quadratics don't do this. And quadratics don't do this. So lots of functions are not linear transformations. I would in fact say most functions are not linear transformations. Linear transformations are extremely special functions. So please don't just assume that because this is a course in which we're going to make powerful use of linear transformations that every function we're going to see is going to be a linear transformation. It's absolutely not. We're going to see lots of not linear transformations. So here's an easy example. There's a perfectly innocent function from R2 to R2. It's not a linear transformation. If you try to prove, like we did just a second ago, if you try to go through and prove this is a linear transformation, you will fail. Here's how I know you will fail. These two things should equal to each other. Right? By linearity. Linear combination in, linear combination out. These ought to be the same things. But if you multiply, add, plug in, blah, blah, work it out, you can see that these two things are not equal to each other. So, not a linear transformation. So don't, so be careful. Before you say something's a linear transformation, you better be sure it is, because it might not be. Here's a neat fact. All linear transformations have the feature that they send 0 to 0. Very convenient. The image of 0 is always 0. T of 0 is always 0. The origin goes to the origin. Different ways to say it. It's really easy to prove this fact. Here's an immediate consequence of linearity. Right? You can factor out the 0, you might say. Or, linear transformations play nice with scalar multiplications. Right? And then just observe that, well, that's T of 0, and that's 0. So therefore, we win. Right, so immediate consequence of linearity. Very nice. Okay. So let me remind you of the standard basis vectors. We talked about these back in Chapter 1, but I know it's been a while. Well, it's only been like a week, but but we've covered a lot of material since then. So just as a reminder, these are the standard basis vectors in R3. And it turns out linear transformations have a special relationship with the standard basis vectors. If you take Math 216, we're going to find out that linear transformations have special relationships with all bases. But we haven't defined bases yet, so that'll be a Math 216 thing. But anyway, for the moment, the standard basis vectors, these vectors, there's a special fact involving linear transformation. So here it is. And this is really very surprising. If you have a linear transformation, and if you know the images of the standard basis vectors. Now let me remind you, an image that just means output, right? So T of EI, that says we're going to take these standard basis vectors EI, we're going to plug them into this linear transformation T and see what comes out. So T of EI are, grammatically you would just say the images of the standard basis vectors. Okay. If these are known, if you tell me the values of T at this handful of input vectors, I claim that completely characterizes the linear transformation. In other words, I can tell you all the other values of this function. And it's almost like a magic trick, right? Here's my analogy. I think this is a silly analogy, but imagine someone says, okay, here's a deck of cards. They give you the deck of cards, and they say, shuffle it. Cut it 3, 4, 5 times. Shuffle it a couple, 3, 4 more times. Okay, now tell me the top 3 cards, and now I'm going to tell you all the rest of the cards in order in the deck. That'd be a heck of a magic trick, wouldn't it? That's kind of what this is saying. If you tell me just a few values of these functions, I can tell you all the others. So, wow. Heck of a trick. So it's a really easy proof. Here's the way we do it. Let's suppose we're interested in t of x for some vector x, and suppose x has certain coordinates, x1 through xn. Let me remind you that a vector x1 through xn is a linear combination of the standard basis vectors in a very special way. Right? So this is an observation that we made at some point back in, I think it was one of the exercises in chapter 1. A vector is always a linear combination of the standard basis vectors, and the coordinates of the vector are the coefficients in that linear combination. All right, this is just multiply it out. Easy to confirm this works. But every vector is a linear combination of the standard basis vectors with its coordinates as coefficients in that linear combination. Y'all remember this fact? Okay. So that means this vector x I can rewrite as a linear combination of the standard basis vectors. And then, having done that, I can just apply the linearity. This is a linear transformation, so linear combination in, linear combination out, and I claim we're actually done with the algebra of this proof now. The magic trick is complete. Ta-da! Let me just explain now why I claim that we're actually done. These standard basis vectors, images, are known, so I know what these are. These are given. So if you give me some vector x, you're giving me the coefficients that will allow me to compute t of x explicitly. There's a formula, right? If I know what these yellow image standard basis vector images are, if I know those yellow vectors, you give me a green vector, I punch it up per the box, purple box there, and I compute t of x. So the value of t can be computed for any vector x. So, neat fact. Cool magic trick. Now, how do you interpret this fact? Well, this algebra is invaluable. This is really important algebra, and we're going to be using this algebra an awful lot. So get ready for that. But here's the way I like to think about it. This is a very powerful property for a function to have. And we get this property merely by knowing that it's a linear transformation. I view this as being evidence of how few linear transformations there are. How most functions are not linear transformations. Because if there was lots of different functions that were linear transformations, then how could this be possible? That's just how I think of that. Okay. All right. Here's a picture of what we just talked about. Here's our standard basis vectors, right? Suppose I know those images. Suppose I know the images of the standard basis vectors. Well, then whatever vector you give me, I claim I can compute its image. And, of course, the way I do it is by realizing that, well, look, this vector, obviously it's a linear combination of the standard basis vectors. And so I just use those coefficients to compute that by way of the same linear combination on the outside. So you can see where the linearity is used. If once I view the input as a linear combination, then I can compute the output as a linear combination. In fact, this picture might look familiar. This picture looks kind of like the picture that we wrote down when we were defining what is a linear transformation, right? And that's kind of suggestive of the big point here is that the reason this fact is true is because of linearity. It is the linearity that makes this work out. Okay, so just to give you a little bit of geometric intuition, I like this statement here. Linear transformations deform the domain in a uniform way. There is a uniformity to how linear transformations deform the domain. So here's a linear transformation from R2 to R2, and as I've drawn it here, T of E1 is that, and T of E2 is that. Okay, and everything else kind of does what it has to. I mean, if I know where T of E1 and T of E2 go, then everything else goes to kind of where it sort of has to go. And a consequence of this that requires a little bit of algebra, but this is something that y'all can do, is this uniformity of deformation. So in the following way, these lines here in the domain are all parallel. They're images over here in the target, all parallel. Right, so everything's kind of gotten turned, among other things, but everything's been turned the same amount. Everybody see what I'm talking about there? This is sort of a uniformity. Here's another way I like to represent this. Suppose, and I'm going to zoom in for easier drawing purposes. Suppose I have some figure here. I'm going to draw a little happy face. Right now, that happy face, if you look at how the image on the left has been deformed, it's not just a rotation. You could say it's a rotation, and then it's been sort of stretched left to right. Or differently, you might say we started off by taking the original image and kind of doing a shearing kind of it, and then rotating the shearing. Different ways that you could think about what's happened here. But anyway, that face maybe gets deformed into something like, okay, let me see if I can draw this. Something kind of like, maybe something kind of like that. Right? What I mean by the uniformity of the deformation is that if I were to take this thing in the domain and maybe move it over to there, the image would move, but it would still look exactly the same, right? So the way this part of the domain is getting deformed, as you can see here, right, is exactly the same as the way this part of the domain is getting deformed, as evidenced by that being the same deformed happy face. Okay, so anyway, that's a different way to think about linear transformations. By the way, this is a nice exercise for y'all to try to prove. You have all the tools that you need to do it. Suppose that two lines in the domain of a linear transformation are parallel. Show that their images, if the images are lines, and by the way, the images are either lines or points. It's possible that they're just points. But if their images are lines also, those image lines are also parallel. It's a perfectly reasonable exercise. In fact, I don't remember, but I might have made that an assigned exercise at the end of the section. If it's not, I think it's a fantastic little practice problem. Think about how linearity forces parallel to go to parallel. It's an immediate application of linearity. Okay. Hint: parameterize these lines and then plug into the linear transformation. Okay, some examples. Here's a linear transformation. So this is from R2 to R3. Now notice I've drawn here my domain is R2, my target is R3. And I'm not going to tell you the formula for this function, but I'm going to tell you what T of E1 is. I'm going to tell you what T of E2 is. E1 has this image, 1, 2, 1. And E2 has this image, -1, -1, 3. And I've drawn the little dotted lines are my effort to help you visualize, my poor attempt to pretend that this is a three-dimensional figure. Right? Again, always hard to do with two-dimensional paper. Make it look like a three-dimensional figure. So the dotted lines are just supposed to help with that. Okay, so that's all I'm going to tell you about this function. And it'd be tempting to say, well, I don't know very much about this function because, well, I only know two values of it. But I know the values of this function on all of the standard basis vectors for the domain. Domain's just R2. The only standard basis vectors are E1 and E2. And I know their images, and therefore I know the image of everything else. Right? So for example, if you were to take, what about this vector? What about E1 plus E2? Well, by linearity, its image is T of E1 plus T of E2. And in fact, every vector in this plane, in the domain, being as it is a linear combination of E1 and E2, is going to have an image that is some sort of linear combination of those two vectors. And so just knowing those two output vectors, I know that the image of this whole linear transformation is, it's this plane. It's the unique plane going through the origin that's parallel to those two vectors. Yeah? Everybody on board? Okay. There's a lot of examples in this section, by the way. So I'm going to let y'all read some of them. I'm going to do a couple more. But there are a few that I'm going to leave for y'all to read. Here's an interesting one. A little formula there. You can check for yourselves that this is a linear transformation. Again, it's just a little bit of tedious. It's not even that tedious, right? But there's some brute force algebra that will confirm that this is a linear transformation. Okay. Let's try to understand geometrically what this function does. Okay. Well, I'm going to take this formula, and into it, I'm going to plug the standard basis vectors. What happens to E1? Keep in mind, E1 is 1, 0. Right? So if I plug in, 1, 0, well, the image is negative 0, 1, otherwise known as 0, 1. And so its image is that. All right, now next question. What happens to that vector, E2, otherwise known as 0, 1? Okay, 0, 1. Let's come up here. 0, 1. I'm going to get negative 1, 0. Okay, let's come down here. Negative 1, 0 is that vector. Right, so interestingly, what's happened, both of these standard basis vectors have been rotated pi over 2 counterclockwise. Well, everything else in the domain is a linear combination of those, and I appeal to your geometric intuition. I can just imagine this entire picture, right? The two standard basis vectors, this x that is a linear combination of them, the rectangle that I use to represent that linear combination, the whole picture. If I just rotate that whole picture, right, then I get that T of x is, well, it's the exact same linear combination of the rotated images, and therefore it is itself just the rotation. It is a 90-degree counterclockwise rotation. So all of the vectors have been rotated 90 degrees counterclockwise. So that's what this function does. This function here, this that we checked first was a linear transformation. Now we have a really, natural geometric interpretation of it. This is a rotation. Everybody good? Okay. It turns out that all rotations around the origin are linear transformations. This isn't too terribly hard to argue. Let me draw a picture. If you have a a rotation, and if here's a couple of input vectors, and here's a linear combination of them, and here is a parallelogram that kind of describes how that's a linear combination. That was not good art. Let me try that again. Okay, good enough. So I have a couple of vectors. I have a linear combination. I appeal to your geometric intuition. If I were to just take that entire parallelogram and rotate it, then I would have both the otherwise images, namely the otherwise rotations, and I would have the rotation of the linear combination, all from the exact same picture, the exact same parallelogram. Therefore, the linear combination that we need still holds because, well, I rotated the entire parallelogram. Okay? So I claim all rotations around the origin, per this argument, are linear transformations. Okay. That ends up giving us a powerful result. Suppose all I know about a function is that it is a rotation in R2 around the origin, counterclockwise by some angle, theta. Suppose I want to find a formula for that. Right now, I want you to think back to high school, think back to trig class. How would you find a formula for a rotation by some angle, around the origin? And what you would probably do is think, okay, well, here's a vector x comma y, and if I rotate by some angle theta, if that angle is theta, and if I know that that angle is, I don't know, maybe alpha, and you'd be drawing triangles like this one and that one, and then you'd probably have to drop a perpendicular and do that, and you'd have a nasty little problem of computing lengths of a bunch of different things, and it'd be annoying and hard. Okay. So we're going to be able to understand this in a much easier way as follows. We just argued rotations are linear transformations. You can't make that argument in high school because you don't know what a linear transformation is. We know it's a linear transformation. We also know that linear transformations are entirely characterized by what happens to the standard basis vectors. So if I want to understand this rotation, all I really need to do is understand what happens when I rotate the standard basis vectors. What happens when you rotate E1? What happens when you rotate E2? And those are easy trig problems. Right, look at this right here. If you take E1 and if you rotate it by an angle theta, look at the image of E1. Here's an easy right triangle to understand. Oh, whoops, missed. Let's try that again. Easy right triangle to understand. Right, we know that distance is 1. The hypotenuse is 1. The coordinates are just cosine and sine of theta. Very easy. Super easy trig. Right? Not terribly differently. If I look at E2, look at the rotation of E2, look at this right triangle, and you got to think about the cosine and sine, but which ones are which, and there's a minus sign involved because this triangle isn't, the angle theta is not measured from the positive part of the x-axis here. So, you got to apply the trig appropriately, but it's a pretty basic trig that you can write there, and you can compute TV2. It pretty much involves sines and cosines and an appropriately placed negative. So, easy calculations allow you to conclude the images of the standard basis vectors. That does all the work for us then. Linearity tells me that whatever I want to rotate, it's going to be a combination of the rotations of the standard basis vectors. We just got through computing those two things, and out comes our complete formula for how to compute that rotation. This will rotate any vector in R2. So we used a little bit of high school trig here in order to do this, but what was the powerful tool here was the idea of the linear transformation, the idea that that linear transform. What is a linear transformation, and how powerfully it is characterized by simple observations. Okay, so this would have been a tremendously difficult problem in a high school algebra course, high school trig course. It's an exercise in multivariable in linear algebra. It's really linear algebra. Okay. All right, there's a few other examples. Again, I'm going to suggest that y'all read on your own. I'm going to move on now to the section on matrices, section 3.2. This is really just a continuation of linear transformations. And here's a linear transformation. By the way, you'll recognize this is the exact function that we wrote as a linear transformation. The start of the lecture, was near the start of the lecture. So it's a linear transformation. Cool. We know we made a big deal out of the fact that you can characterize that simply by knowing the images of the standard basis vectors, right? If you know T of E1 and if you know T of E2, and by way of the fact that you know that this is a linear transformation, that's all you really need to write down. So neat sort of alluring potential for shorthand is I don't actually have to tell you this formula. If I want to describe this function t, I don't have to, bluntly write down the whole formula. If I just tell you what are these two vectors and say linear transformation, that does the job. Right? Okay, so here's the shorthand convention that we're going to use. Since all I have to tell you is what those two vectors are, the convention is going to be that first vector, the image of the first standard basis vector. I'm going to make it the first column. The second vector, the image of the second standard basis vector. I'm going to make that the second column. And then this matrix will be our shorthand representing that linear transformation. All right, it's a convention, it's a choice. But this little shorthand that I have down here, this little matrix with columns being 2, 1, 0 and 1, negative 3, 5, all the information that you need to reproduce that formula for the linear transformation is right there. The first column, by convention, being the image of the first standard basis vector, the second column being the image of the second standard basis vector, linearity combining with those, you reproduce that formula. Everybody on board? Okay. Now I have a question for y'all. A lot of you have seen matrices before, and a lot of you have seen formulas for how to multiply two matrices, how to multiply a matrix times a vector, that kind of thing. So I'm just curious, show of hands, how many people have seen, for example, how to multiply two matrices to each other? Okay, all right. How many people have seen a compelling argument for why that should be the formula for how to multiply two matrices? And that's what I thought. Okay, no undergraduate, pre-linear algebra that I've seen has ever seen a compelling argument for it, because it's not a reasonable thing to do in a high school course. Right? In order to make a really good argument, in my opinion, a really good argument for why matrix multiplication should follow that formula, you need to understand matrices from the point of view of linear transformations, and of course, linear transformations can't be presented in a high school argument. I practically never, it's effectively never done in a high school setting. Okay, so we have that opportunity now, and that's going to be kind of my goal for the rest of the lecture to show you, why is matrix multiplication what it is. Now, so for those of you who have seen matrix multiplication before, I want you to take that knowledge, I want you to kind of set it aside. Obviously don't forget it, don't throw it away. That's somewhat useful. That experience is going to have some value. But I don't want you to proceed through this lecture with that knowledge in mind, right? Because I want to rediscover that in the way I want to present it, which I think is going to be really natural. If you have not seen matrix multiplication before, how convenient, right? It'll be very easy for you to not think about any previous knowledge while I'm presenting in a new way. Okay. All right. So, just to start off with, let me just remind you. So we have kind of a new definition of a matrix. By the way, has anyone ever had a definition of a matrix before? Sometimes a matrix is just presented as, well, it's an array of numbers. It just is. And that's what I was told, right? Is that it's just an array of numbers. which I suppose technically it is, but it leaves the listener begging for, and why would we be interested in arranging numbers in an array like this, right? So I'd be willing to bet most of you have probably not gotten a motivation for why would we even want to talk about a matrix. And I've already kind of given this to y'all. My point of view, my favorite point of view, is that we should think of a matrix as being a shorthand representing a linear transformation. Okay. We write it as an array of numbers because that's a way to conveniently shorthand a linear transformation. There are other motivations, by the way, in Math 216, which I guess a lot of y'all are going to take. Show of hands, Math 216 in the fall? Not that many. Okay, anyway, for those of you who will be joining me in Math 216 in the fall, we're going to take a different motivation for that, for what is a matrix, because of the way the textbook presents it. That textbook does it differently. And so, my hands are kind of tied. But anyway, this is my personal favorite. Yeah. Okay. Okay, so a matrix represents a linear transformation by its columns being the images of the standard basis vectors. That's our definition that we're going to go with. So, two big things to remember. For one thing, it's a shorthand representing a linear transformation. Secondly, and the one that we're really going to, this is a big deal, we're going to use a lot, the columns are the images of the standard basis vectors. And you can see it in how I've written it down there, but make sure to reiterate to yourself, memorize, deeply memorize this phrase. The columns are the images of the standard basis vectors. All right, that's the convention by which we make this shorthand. Okay, so a couple of quick examples. Here's a linear transformation. How would I represent it in a shorthand? Now, I'm just going to follow the rules. E1 has that image. And you plug in 1, 0, 0. Out comes 2, 1. Okay. E2. Out comes 0, 3, etc. So you have these three images of the standard basis vectors, and those are the three columns that we make, and therefore this is the matrix that represents that linear transformation. Everybody see how that works? It's real easy to do. Just plug in the standard basis vectors, see what drops out, put those into the columns. Okay, working backwards. We've already kind of done a question like this before, but just not in this language. Suppose I know a matrix. If I want to reproduce, what is the corresponding linear transformation? How do I do that? Okay, well, step one, realize that the columns are the images of the standard basis vectors. Now, again, I can't emphasize that enough. Go back to our definition here. This is the phrase that I want you all to have ingrained in your minds. The columns are the images of the standard basis vectors. Okay. And so here's the part of the problem we've already done before. If you know the images of the standard basis vectors, then keeping in mind that X is a linear combination of the standard basis vectors by way of its coordinates, then you can compute T of X as that linear combination, namely that linear combination. Namely, you get this. All right, so it's just a matter of capitalizing on the linearity, and there's your formula for T of X. Yeah, everybody good? Okay. So a matrix is a shorthand for a linear transformation. I want it to be a little bit more than a shorthand. Turns out to be very convenient to have further shorthands, you might say. So what I'd like to do is I'd like to think of a matrix not simply as a shorthand representing a linear transformation. I'd like to think of a matrix as an object on its own that can do its own things. Right? But that said, as we have this matrix on its own, thought of as doing its own things, let's not forget where it came from. That matrix, what it is it's just a way of representing a linear transformation. So when a matrix does things, don't ever forget, a matrix doing something should be thought of as the linear transformation doing those, because that's what the matrix represents. Right? Okay, so with that in mind, let's ask the question, what should it mean to multiply a matrix times a vector? Right? Now, again, some of y'all in your high school courses might have seen a rule. Here's the formula for how to multiply a matrix times a vector. Don't ask why. Right? That's what I was told. So I'm going to show you what I'm going to call why we multiply matrices by vectors in certain ways, and it comes down to what I was just saying. If I want to multiply a matrix times a vector, let's say the matrix is called A, and I want to multiply it by some vector called X. Don't forget about the fact that matrix is simply a shorthand representing T. So what the matrix does to X really ought to be what T does to X. So A times X ought to be, if a shorthand is a shorthand, if it is in fact representing T, A times X really ought to be T of X. Yeah? Let me take a pause on that. Does anyone have any questions about, does that seem like a plausible motivation? And it turns out that if you take this motivation, this gives us exactly the formula that those of you who have seen it in high school saw. So here's the argument. Right. But by the way, this statement I summarized. This is what I call interpretation 0. If you want, you can think of this just as a motivation. The incentive that we have for all the results we're about to derive is that I would like for a matrix vector product to be just the action of what does a linear transformation do? Because that's what matrices are. Okay, so here we go. Let's think about this matrix A. I'm going to need to make reference to the columns. So this is just a notational thing. Let me just choose, whatever matrix I have. I'm just going to give the following names A1 through AN to those columns. Okay. I want to multiply by this vector X. I need to have names for its coordinates, so no surprise. Let's call them X1 through Xn. Okay. All right. And by the way, don't forget, our big rule about matrices is that the columns are the images of the standard basis vectors. That is always true. That's the definition of a matrix. Right? It's the shorthand by which the columns are the images of the standard basis vectors. Okay. So I claim that this choice that we've made here, I would like for matrix vector multiplication to come out of the action of the linear transformation. Dictates what the formula for matrix vector multiplication has to be. It has to be as follows. That's what we're starting with. Don't forget X is a linear combination and T is linear. So I can rewrite T of X like that. Don't forget that the columns are the images of the standard basis vectors. So I don't really have any choice in the matter, right? If I insist that A does what T does, this tells me that I have to use this formula for matrix vector multiplication. If you want to multiply a matrix times a vector, you have to do as follows. The formula is that you take the columns of the matrix and you do a linear combination using the coefficients using the coordinates, I should say, of the vector x. That's what it is. That may not be the formula that you saw in high school, but this is an equivalent formula. I'll get to the formula, the high school formula that you saw, in a couple seconds. Yeah.
That's just a vector after you.
Yeah, that's right. This is a vector. So notice that a1 through an are vectors, right? And when you take those vectors, when you multiply them by scalars, these are vectors, right? And then when you add a bunch of vectors, you get a vector. Yep. Okay. So yeah, so matrix times vector is vector. Okay. Which, by the way, of course, it really should be. Let's not lose sight of the fact that what this linear transformation T does is T is a linear transformation from Rn to Rm. So if I want T of x, if I want Ax to be T of x, well, T of x is over there. T of x is definitely a vector in Rm. Therefore, Ax has to be also that same vector in Rm. Yeah? Everybody happy? Great question. Okay. All right. So this gives me my what I'm going to call my definition here. This definition of matrix vector multiplication. It's just this formula that we just derived, which again comes out of. It's an immediate consequence of. Hey man, matrices are shorthands for linear transformations. Therefore, I have to make this choice effectively. Okay. All right, and now here's a way to think about it. And so I hope you'll memorize this formula. Here, let me circle the whole thing. I hope you'll memorize that formula, but here is a nice sort of rolls off the tongue interpretation. And that is, when you do a matrix vector product, you're taking a linear combination of the columns of the matrix where the components of the vector are your coefficients. Right, so coming up to the formula here, we're taking these column vectors, we're taking a linear combination of those columns, and we're using the components of the vector as our coefficients. Everybody happy with that? So visually, I think this is a nice way to think about it. If you want to do this multiplication, just take the columns. You can see the columns. Look at those columns. Take a linear combination of those columns. The vector that you're multiplying by gives you your coefficients. Okay. All right. So that's the process. Now, I know this isn't the formula you saw in high school. The formula you saw in high school was this one, probably. That the way you do a matrix vector product is one coordinate at a time. You compute the first coordinate of the product vector by doing a dot product of x with the first row of the matrix. Right? Does this look familiar? Right? And if you want to compute the second entry, then you take the second row, dot the vector, etc. It turns out that's, in fact, exactly equivalent. And let me try to persuade you of why it is. I mean, it's a matter of writing down the algebra. But here's a way to think about it. Let's look at this product here. And let's compute these results one coordinate at a time. How would I compute the first coordinate using the linear combinations point of view? Forget about the old high school dot product formula. I want to use the linear combinations point of view. How would I compute the first coordinate? Well, the first coordinate of that linear combination, I compute this as a linear combination of these. So I compute its first coordinate by looking at the appropriate linear combination of the first coordinates. In other words, I compute that entry as a dot product. Just like that formula there. Yeah. Okay, so it's equivalent. Now, there is a tendency for students at a time like this to say, oh, good, the new, unfamiliar, seemingly fairly inconvenient formula that Bray just presented, it's exactly the same as the good old handy-dandy convenient formula that I'm already accustomed to from high school. I'm just going to do it this way. Strong tendency to think in terms of those, in terms of that reasoning. Let me try to pull you away from that reasoning. In high school, there's a very limited number of things that they ask you to do with matrices. Mostly it's arithmetic, right? So they give you, here's a matrix, here's a vector, multiply them. And the answer is a column of numbers. It's just the arithmetic only, right? So now let me grant you that if your goal is simply to do arithmetic, then yeah, you can't beat this. This is awesome. That's why they show you this in high school. It's a computational super slick. No contest. Okay. Well, we're doing much more than just computing with numbers, right? Let me make the I made this observation at the start of class. Wolfram Alpha will do that for you, right? So why are we trying to compete with Wolfram Alpha? Let me rephrase that. Why should our only goal in a math class be to try to beat Wolfram Alpha? That's a loser. We're never going to beat Wolfram Alpha at arithmetic, right? So the reason that this formula here is not good enough is that it's limited. It's great for arithmetic, but it only has certain applications. It only shows certain connections between ideas. It is useful to realize that matrix vector multiplication involves dot products with row vectors. There's an idea there. That's a connection between one idea and other ideas. Very cool. Cool stuff can happen. But it's limited. It's just that one connection. This over here is a different connection of ideas. This says that matrix vector multiplication can be thought of as linear combinations. And it's going to turn out, and we're going to see this both in this course and then to great degree in Math 216 as well. We're going to see that the connection between matrix vector multiplication and linear combinations, and therefore the connection to linear transformations, is really powerful. Right? So this fact, the fact that you can the process that you are perhaps inclined to think of as being an arithmetic process, it's not. It's an algebraic process, and the algebra, this point of view on the algebra, ends up being a really big deal. Okay, so if you try to get through life with just this, you're going to find yourself without the necessary tools. It's very important to have this tool also. Right? Hammers and screwdrivers are different things. You can't just say, I'm already good at hammers, I'm just going to use hammers. They don't work with screws very well. Does that make sense? All right. Okay, moving along. So here's how you compute a matrix vector product. I'm going to do it two different ways. As a linear combination of the column vectors. There's the column vectors. The coefficients are the coordinates of the vector I'm multiplying by. Punch that up. There's your product. On the other hand, now here's the old high school point of view on how to multiply. This vector, I can dot to get that number. Dotting with the vector on the right. This vector, I can dot with the vector on the right to get that. And this row vector, I can dot with the vector on the right to get that. It's not even terribly different arithmetic if you think about it. Let me just point out, and I've already kind of made this observation, but let's look at specifically what happened in computing this first coordinate and computing this 16. Where did that 16 come from? Well, on the one hand, you can think of that 16 as having come from 921.123. But notice in this calculation up here, 921.123. It's the exact same arithmetic. Okay. All right. Okay. So Next question, what should it mean to add two matrices? There's a similar question. What should it mean to multiply a scalar times a matrix? We're a little short on time, so I'm going to skip over these. But I want to point out that the choice that we're going to make for both of these questions, for example, what should it mean to add two matrices, is going to come down to, just like when we were adding vectors. When we faced, first day of class, when we faced the question of how should we add two vectors, what we did was we said, well, what do these vectors represent? And those things that they represent, like displacements, what should it mean to add two displacements? We came up with a natural interpretation of what it ought to mean to add two displacements, and then we used that as our motivation to define adding two vectors. So same thing here. What should it mean to add two matrices? Well, don't forget, matrices represent linear transformations. So when I add two matrices, I'd better think of that as adding the two corresponding linear transformations. In other words, adding these two functions. T is a function, S is a function. Okay. And then if you just take that as the given, and if you compute one column at a time, don't forget the columns are the images of the standard basis vectors. The columns of the matrix are the images of the standard basis vectors of the linear transformation. That's the definition of a matrix. Here's how you add two functions. You add two functions by adding the output values individually. T is represented by A, S is represented by B, and here we go. We have our formula. It's A, EJ, B, EJ. Well, those are the images of the standard basis vectors, so those are the columns of A and B. So the punchline is the column of the sum of two matrices is the sum of the columns of the original two matrices. So in other words, you add matrices exactly the way you would kind of hope. So for example, if you want to add this and this, well, the first column is just that column plus that column, exactly as you would think. Or even more conveniently, each entry is just the sum of the entries, corresponding entries in the original matrices. So handy dandy. Let's see here. I have 2 seconds left. Okay. All right. I guess this is where we're going to end it for today. I guess I ended up doing that part. We're gonna start next time. I was hoping to get to it today, but we'll start on tomorrow with matrix multiplication and why matrix multiplication should be what it is. Okay. See you later.